Hello, and welcome to our inaugural episode of Our Future in Space. I'm your host, Dr. Jeff Greenblatt, and I'm joined in the studio this morning by Eric Ward, who is the co-host, and Al Globus, our esteemed colleague and guest. Just a short bit about me. I'm the Vice President of Science and Research at Orbital Assembly Corporation, and I also own my own consulting firm, Emerging Futures. I've got a background in chemistry, climate change, energy systems, and of course, space technologies. And Eric, I'll let you introduce yourself.
Yeah, thank you. I'm the Vice President of Engineering Design at Orbital Assembly. I have a background in engineering, and I'm a space systems architect trained at MIT. And I'm really excited for this episode today. We've got Al Globus here to talk about large structures in space that can support human communities. Al, why don't you give us your background?
Oh, well, thank you. I spent 39 years writing contract software at NASA Ames Research Center, and also doing a little bit of space settlement work on the side, which is the stuff I was actually interested in. That work went to two things I think were of some value. One is that there was a contest, a space settlement design contest for kids, and last year in that contest we had, it was like about 3,000 kids involved. Wow. So we hit a lot of people, and we got them across the idea. Gerard O'Neill's big breakthrough, which is that you might not want to live on a planet. You might want to live in a spacecraft orbiting around a planet or a star, something like that. And I spent my 39 years at NASA Ames Research Center. I wrote software for all kinds of vehicles, X-37, shuttle processing. And it was really a lot of fun, but it was time to go, and I'm retired now.
Well, we're glad that you could make some time for us today in your, I'm sure, busy retirement.
My pleasure.
So we're really both thrilled to have you here, and I think maybe let's just start by delving in a little bit to this idea of large-scale space structures. You mentioned Gerard O'Neill and space structures, and assume that the audience doesn't know anything about these. Why don't you give us a little bit of background, Al?
Well, the basic idea is to live inside a gigantic spacecraft. Mm-hmm. And if you do that, some good things happen compared to, say, being on the surface of Mars or surface of the Moon. For one thing, you can build your settlement close to Earth, where logistics are much easier, and that makes a huge difference. You can tell by the delay you have in it when you go try to talk to Mars, and it can rotate to provide any gravity level you like, pseudo-gravity. It's not real gravity, but pseudo-gravity, which means that it's highly likely that your kids will grow up with strong bones and muscles. And that's something we definitely cannot say about growing up in 1/3 G or 1/6 G. Mm-hmm. So those are a couple of the big ones. The other thing is you're not restrained by the environment. For instance, on the Moon, you have a lot of very, very sharp dust, and it gets in everything. I used to have a book. It was this great book. It was about that thick, and it had hundreds of pictures of Apollo astronauts, the ones that didn't make it onto the lecture circuit, and these guys, they're in white suits when they get there, and every single one of these people who had been there for more than an hour was black up to their chest, and the rest gray. And this stuff gets, it's sharp, and it gets stuck in things. You can't get it out. You just can't get it out, and it's really a mess, and you have to deal with it. Well, if you're on orbit, there isn't any dust, right? Of course, there isn't any stuff either, any matter. But, right. But you can get that. You can get materials from asteroids. You can get materials from the Moon. You can get materials from Earth, even. I've forgotten what the question is.
No, that's actually really great. I know a kind of premier design is referred to as the O'Neill cylinder. Maybe you could get into a little more detail for our viewers on what an O'Neill cylinder is.
Well, it's, as you might expect, it's a cylinder and it's very long. Okay, I think if I remember correctly, the numbers are 32 kilometers long and diameter of 8 kilometers. So this is a really big system. It's as large as, there's plenty of people in Manhattan that haven't gone farther from their home in the size of this in a couple of years, And the idea is, and, I can show you some of the features of this. It's got a bunch of communication gear on the end. It's got a whole bunch of little pods going around. Those are the agricultural modules. And that, by the way, is a logistical nightmare. Somebody's going to jump on that and say, "Oh, we can't build." O'Neill considers it's impossible because those little things with the where the agriculture is. Well, it's too much work to get it back and forth. Well, change the design. I mean,
right.
That's simple solutions to this. But in any case, those things are agricultural modules, and in this design, you would have to ship all of the food to those big cylinders where people live, and then when the people were done with them and had stuff to send back and be fertilizer, you'd have to package it all up and move it back. And you probably don't want to do that. You probably want to integrate everything together. But in any case, what you're seeing is the reason it's coupled is when it rotates, that can set up all kinds of forces, and you null them out by having two things rotating in opposite directions. Then you can
because I mean, these structures are in orbit around the sun, just like everything else in the solar system, right? So, in other words, they need to slowly precess over the course of the year to remain pointed at the sun, or why is that a problem when they're rotating?
Then you have to change the angular momentum, and that's expensive. And actually, if you look at these things, it's pretty obvious they must be assuming a fusion energy source, or at least fission, because there are no solar arrays even remotely large enough to get enough energy. And you can see a bunch of stuff on the end that's probably mostly communication gear, and those big sort of somewhat colored things in the back. Those are thermal radiators. Get rid of waste heat because you really don't want to cook.
And what are those long sort of orange? Oh, I'm sorry, Eric.
Go ahead.
Well, so what are those sort of long orange strips that are sticking out from the back of the cylinder?
Those are the thermal arrays.
Those are the thermal arrays.
That's what I would. You got to reject waste heat.
So why so big? You mentioned 32 kilometers and 8 kilometer diameter.
Well, the O'Neill cylinder was an exercise by Dr. O'Neill. It's an exercise in how big a settlement could be, given strength of materials. They were using steel as their strength of materials. This is really interesting because we have to do with cosmic composites to keep the weight down. And SpaceX went in this same rabbit hole. They went in for carbon composites, and it just got messier and messier and harder. And finally, they gave it up and they went with steel. It turns out, in the case of steel, you get if you pick the right steel, you do it just right. As it heats up, it'll actually get stronger, and that's a really nice property.
Yeah.
So he basically calculated that you can get structures that are the size you described, 32 kilometers long, which is about 20 miles, and several kilometers in diameter, which I guess are interior areas like the size of a small city, right? Or even
That's the idea. That's exactly the idea. Is you got to ask yourself, okay, you're going to spend, if you're going to become a space colonist and you're going to have O'Neill cylinders or Kalpana cylinders or Stanford torus or whatever, you're going to be living inside of the spacecraft, and you're going to want to make it as big as you can. I mean, the first ones you're going to make small because good engineering principle, you do incremental development. You build a little, build a little, build a little, build. Okay. But eventually you want to get them to essentially as large as you can get them. So that was the basis of what they were doing.
Right. Because I think unlike even some of the smallest, solid bodies in the solar system, like moons of Jupiter, other places that have enough gravity to keep things in place, maybe similar to the gravity of our moon, we're still talking, millions of square kilometers. So the sizes of countries can be built all in one place. O'Neill cylinders, even the largest ones you're talking about, are still limited to, they're certainly big by today's standards, but they're still small compared to regions on Earth. So there's a bit of a mind shift that presumably happens there.
Well, don't forget that you have to build a pressure vessel no matter where you live. It doesn't matter if you live on the surface, it doesn't matter if you live in orbit. If you're in space, you're going to be living in a pressure vessel. It's just that where that pressure vessel is going to be is going to be sitting on the top of the surface of the moon. Well, that's very convenient for radiation protection. You get a bulldozer and you pile, 5 or 6 meters of material, and voila, you might not get cancer. And you can bury them underground. You can stick it in. There are some exceptions, like lava tubes on the moon. There's ideas for sealing them off and turning them into habitats where you would still be building a pressure vessel, but most of the pressure vessel will be built for you. So, from the point of view of being able to, and now, of course, if you're in a pressure vessel and you can go through an airlock to a different one, then you can expand your size and so forth. But I mean, you're gonna be living in some sort of pressure vessel one way or another. And so there's not that much of an advantage for being on a planet. The big advantage of being on a planet or moon is you get ready access to materials.
Right.
But if you're in the you can imagine building your settlement co-orbiting with the nearest asteroid, and then the settlement just eats the asteroid. Yeah. And when you're done eating the asteroid, then you better have your recycling together.
So you mentioned we're living in a pressure vessel here in space anywhere. When you're talking about a structure, a giant spacecraft like this, like an O'Neill cylinder, what are some of the risks there? What about impact from space debris? Are these, can these be robust, safe structures?
Well, I mean, the larger the settlement, the less likely it is that any particular piece of debris is going to do serious damage, right? Just because of if you've got something that's 32 kilometers by 8 kilometers and you punch a 10-centimeter hole in it, that's one thing. If you have something that's 100 meters along and you punch a hole in it, it's a little more serious.
Yeah,
especially for the people right by the puncture wound, right?
Right.
But
right. I mean, space is a dangerous place. There's no way you're going to get around that. But if you look at the fatalities that have happened in the space program so far, which are all professional astronauts except for one teacher. Well, there's not that much debris if you get well away from Earth. Okay, there's some, but most of it's very small.
Yeah,
and we have the stuff that's getting kind of big. We are building, and we need to build a system for detecting them and then allow them to be diverted. Okay. And the emphasis in that work has to be on detection, because if you detect an asteroid, if you don't detect the asteroid, of course, everything's useless. If you do detect something with the asteroid, you will suddenly find yourself in possession of gigantic piles of funding to build it, the deflection system.
Yeah.
So, now,
hopefully not scrambling after the discovery, but in preparation for a discovery, so that we can then deflect.
And there are people working on this. The B612 organization, and who's had a bunch of people working, and they're trying to get realistic maps and able to predict asteroid position over long periods of time. We've had stuff like that for a while, but it hasn't necessarily taken into account all the factors, particularly the small ones, which build up over time. You get these perturbations; they build up over long periods of time, and then you got yourself, all of a sudden something that wasn't dangerous is dangerous. But I mean, there's advantages and disadvantages. There aren't any earthquakes and there aren't any volcanoes. Okay.
Yeah.
Right.
On the other hand, there's a real shortage of air on the other side of the airlock.
Yeah.
But like you said, even if you poke a sizable hole, 10 centimeters or so, like that doesn't spell instant death for the residents, and even folks sitting right there, can quickly run away from the point of impact, and it's not like they get sucked out the airlock like they show in the science fiction movies, right? I mean, this takes a long time to empty. Like,
especially for a large habitat. Yeah.
There's a sci-fi book. It's like 7 Eves, I think is the name of it. And one of the things that keeps coming up over and over again is you punch a hole in the side, and it takes a while.
Yeah.
It doesn't like all rush out instantly and you blow up like that. There was a movie with the original James Bond. What was his name? Oh,
Oh, yeah, a while ago.
Well, going way back there before
yeah.
Sean
In any
Connery.
case, in there he opens up a thing and the guy explodes. From the air pressure in the inside.
Well,
Yeah, it's
another
nice to
reason
see.
why to build these, another reason why we should build these as large as possible, right? Others
Yes.
notwithstanding.
I mean, you got to build. I mean, you're not. I mean, 30. If you had to live in 32 kilometers by 8 kilometers, and you weren't getting out, it would feel a little claustrophobic. I would think. It depends on your personality type, but that's a pretty small playground if you're going to really spend all your life in there. Now, of course, you
Well,
can fly multiple O'Neill cylinders or any other settlement relatively close to each other. You follow them in orbit, and there's not that much energy to move back and forth. And you got a lot of energy anyways because you got the whole sun blazing away, right?
Yeah.
So
right, in terms of
and
solar
there
power.
you can go to whole other things. You can have one that's always set up for skiing, and another one that's always set up for surfing. And
Right.
you can tell what I like to do, right?
So yeah, I mean, we were going to get to this in a few minutes. So the idea that you don't just build one and put, all the humans in that. I mean, if we're talking about large scale migration in the solar system, you would probably have thousands of these. Maybe they would be, or if not millions, right? Because so maybe you've done this math, and I think I know the answer from some of the work I've done, but how many people could we realistically fit in an O'Neill cylinder and still have a comfortable amount of space for everyone?
I don't know. That's a number I haven't looked at very carefully. There is in one of the papers that's on the web, there is a mass model, a mass and population model. Just a spreadsheet where you can calculate these make simple sorts of direct calculations. But I haven't looked at it for a while, so I'm not going to say anything too much about it for fear of being wrong.
Yeah. Well, I can tell you from the research that I've done that it depends a lot on your assumptions of how much land you want everybody to have access to on average. So you can certainly build a Manhattan style, high density cylinder, maybe with a large central park, but there would be room for a couple million people. Whereas if you have something which is more like the English countryside with manor houses and a few small towns, it's a few thousand. But the point is, it's not 9 billion humans, which is about what we're going to have, soon on Earth. You're going to need many of these.
Yeah. I mean, that is the idea, and the idea is not to necessarily even be limited to this solar system. It's hard. It's very, very difficult, but you can at least imagine generation ships. If you've been living in something like what you're seeing on the screen now, if you've been living in it for 4 or 5 generations. Does it really matter a whole heck of a lot if your cylinders that are traveling in a group are next to Sol or they're on their way to Alpha Centauri? I mean, yes, it does make a difference, but it's not like you have no other friends to,
Sure.
If you screw things up in one settlement, you can move to the next.
Well, what's so amazing to me is that when I first discovered these structures, this was later in my life. I didn't read about it as a kid, but it was as already a professional scientist. And I was just amazed that it was possible to build something that would be so Earth-like in so many ways, even though it could be physically located, around the moon, around Neptune, or in interstellar space, like you're describing. And of course, there's, you would obviously have to have a very powerful and long-lasting power source for something like that if you're far from the sun. But the point is that you can provide all the sort of normal creature comforts, including gravity and fresh water and open space that we enjoy here on Earth, but it's in an artificial habitat, and it really opens up the universe for exploration and settlement.
Well, it may be. I mean, it's pretty easy to see. Well, easy. It's it's extraordinarily difficult, but quite imaginable to think about. Building thousands and thousands of O'Neill cylinders or something vaguely similar. If you can build one, you can build two. If you can build two, you can build 5, and so on, and so on. So you can grow quite large. You do want to get good at recycling, but there'll be a very strong incentive to do that. And the power source, as you head farther and farther out away from Sol, your power is more and more of an issue. And a lot of the speculation I've seen about it is that you could harvest hydrogen of various flavors of hydrogen and helium from the gas giants and burn them in nuclear reactors. And this would be something we probably wouldn't get around to doing for, I don't know, 500 to 1,000 years. A long time. Plenty, so we can't do that now. But I mean, think 100 years ago. Think 200 years ago, and look at the unbelievably amazing stuff we have done. Just astounding.
Oh, it's amazing.
And if anything, it's going to go quicker.
Right? Absolutely, yeah.
So if we can't do it now, that's unfortunate. But perhaps we'll get around to it in a few years, a couple of decades, or something like that.
It certainly provides a roadmap so that we're not sort of limited to only building a few of these huddled close to the sun. I mean, we have options as we decide to expand outwards as a species. So I don't know if you had another question, Eric.
You mentioned recycling is going to be important. Power source. We've talked about space debris. What are some of the other technical hurdles in designing a habitat like this, and then building and operating them?
Well, the number one problem is launch. Okay? The good thing about launch is there's very sharp and extremely rich people who are working to solve that problem.
Yeah.
Okay. So that's the first. I believe the second, I think almost everybody would agree with that. The second most difficult problem, and here I may get disagreement, is the life support system. You can't have like the shuttle. You bring up food and you eat it, and when it's gone, you better be able to get back. But that's not going to work for O'Neill cylinder with a population of 50,000 or whatever. You need to do what land does, which is grow food on it.
And in a way, take Earth out of the loop then.
Yes.
Right.
Exactly.
As much as possible, and eventually completely, so that you can be self-sufficient.
Well, and people have done sufficient experimentation to know that it's pretty clear that you can, it's difficult, but you can live in an isolated environment. And the big breakthrough there, and they were good at life support systems, but boy, were they bad at marketing. Biosphere 2. And Biosphere 2, for anybody who is not familiar with it, is in Arizona. It was a closed environment. It did not leak much air. And we know this to be a fact because of one of the things that people complain about it. And that is, because you can, if you just look at it, you can't tell if there's gas going in or gas going out, or in what quantities. But we have one irrefutable proof that it was closed, and that was that they ran low on oxygen. And ran so low on oxygen, it affected their mind.
Yeah.
And that could not happen if it was not gas tight.
And if I recall correctly, that wasn't even a balance problem with the humans and the plants, but it was a technical issue with the concrete drying, sucking up oxygen or something like that.
Yes.
And so that proves that even in a gas tight thing, they probably had that balance of plants and human life correct even, and that's possible.
Yeah. I mean, the problem was, if I understand it exactly, was that there was a sealant that needed to be put on the concrete. Otherwise, it would absorb oxygen from the atmosphere. Now, some of the people that worked on Biosphere 2 are going to be at the ISTC, the International Space Development Conference, which, Truth in Advertising, I'm one of the session chairs. Actually, the session chair with the Biosphere folks in it. And these are not the people that did the original study. This is a new group of folks using the same facility, and it's a good place to get those sorts of questions answered.
Yeah.
But in any case,
okay. So,
go ahead.
Yeah. So all right. So we've established launch, bioregenerative or closed loop life support. What about just the sheer challenge of building these huge structures, or maybe that isn't the next most challenging thing on your list? Is there anything else we should think about?
Well, okay, this system is an engineer's dream. I mean, an engineer likes nothing so much as a problem that they can solve. Okay? There's nothing that will make an engineer happier. Okay, and there are going to be hundreds, if not thousands, of engineering class problems, we're pretty sure that the science is going to be okay. You know, we don't need any new physics, we don't need any new chemistry or anything like that. We're pretty sure that's going to work. But we really are not sure is we're going to be able to pull it off. Now, somebody will be able to pull it off, but maybe not necessarily the people that you would think about it. So, so there's going to be lots and lots of problems. And one of them is just the construction. And there's been a little bit of work on there. There's one with a rig that they sort of rotates through. It's doing a Stanford torus and rotates through and builds the same thing over and over again. My favorite is just little very simple robots that assemble it in great numbers. And then when you're done assembling and then you leave some of them there for doing repairs, and you take a bunch of them to the next habitat. But you know, whether that's going to be something that really works very well or not, hard to tell. I think the launch and life support is going to keep us busy for a bit.
Sure, and we're also not going to build multi-kilometer structures right out of the gate. We're going to build something much smaller as a demonstration, and I would imagine it would also cost a whole heck of a lot less to get up there. Because the other thing we're not talking about is how can we ever pay for this, right? I mean, it's much more expensive to live in a space community than on Earth, and it will probably be that way for quite some time. Do you think?
Yeah, definitely. Well, the only thing I can say is I did some calculations, making some very optimistic but not completely idiotic assumptions about cost of various things. And if you build sort of the smallest viable settlement,
okay,
it's going to be somewhere on the order of 100 meters long and about 100 meters in diameter.
I'm going to bring up an image, Al. I don't know if this is close to what you're talking about.
Yeah, this is. There's no scale on it, so you can't really tell how big it is. But you can, and it also is using fusion. Although I wasn't thinking of that at the time that we did this. I did this particular study with a couple of students from India that came here on the Space Settlement Design Contest. They were after it. So yeah, something like this. So it'd be about 100 meters by 100 meters. Which is about the International Space Station has also got a 100-meter scale, but it's just in one dimension. Yeah, this one long thing.
Right. There's a lot of area in there. You know.
What's that?
I said so. There's a lot of living area in there.
There's quite a bit of living area. So in any case, if you take this path, it turns out that you can build this very inexpensively because you don't need. If you put it in the right place in low Earth orbit. Doesn't look like you need radiation shielding. And if anybody goes back to the old studies in the 70s, great studies, by the way, it's overwhelming that the big problem is the radiation shielding, launching it. It takes millions of tons to supply radiation shielding for the Stanford torus, which is a torus about a mile across. Okay? Millions of tons of material have to be launched from somewhere. And so they thought, well, it's too much for Earth. We'll get it from the moon. Well, that's great, except now you need a whole moon development and extraction and processing facility, which is this huge extra piece of work. Okay, you've got it wrong when you're engineering a product, and it gets bigger and bigger, and you can't control it. You know you're in tough bits. And on the other hand, is if you're going along and you see whole swaths of work that don't have to be done anymore, then you know you're onto something. You know, not doing any work at all is always better. I'm sorry, what?
So you've taken a huge part of the engineering problem off the table by placing this in an orbit where the radiation is much less.
Yeah.
Right.
And I did some calculations with Alteris. Alteris is a web front end for some Air Force radiation codes. And it has the property that if you give Alteris it's available to any legal U.S. citizen, a citizen or resident. You know, as long as you're legal, that's all.
Okay.
I'm sorry, I've lost your train of thought.
So I think you were using the code to calculate the radiation dose.
Oh, yeah.
And I want to ask you also how much radiation there is in space that we need to worry about. But tell me this story first, then.
Oh, well, yeah. So So you give it an orbit, an amount of shielding, the material the shielding is made out of, and a date, because the radiation is different all the time, right? And so I picked a year that was really bad, okay? And basically what you're trying to do, so that's one question, is how do you find it? And it turns out that at 500 kilometers up in a circular orbit, you can get down to below 20 millisieverts per year.
Now you're going to have to define that for us.
Yeah, a sievert is a measure of damage, biological or materials damage done by radiation. Okay. Milli, of course, means 1,000th.
Yeah.
And the reason that it came out to that particular number is it turns out there's a lot of arbitrariness in the I should play this back. The first thing I did is I went out. I got to find out how much radiation is acceptable. I wonder what the occupational standards are. And it turns out the occupational standards for like X-ray technicians and nuclear power plant operators and stuff is 20 millisieverts per year. And I found that very quickly. And then I thought, oh wow, I can go on. And then I thought, no. The whole I discovered that using Altaris, I discovered that at 500 kilometer circular orbit on a bad year, 20 millisieverts is sufficient. And it turns out that you can find an orbit like that around Kalpana 1 or Kalpana 2, Kalpana 2 rather. And but I thought, wait a minute, I can't pin the whole project on a couple of hours with a book or two. Okay, that's unacceptable. So I kind of went overboard. I spent 2 years, nights and weekends, reading some of the most boring, imaginable stuff you can possibly think of, but essential. And at the end of the day, I came up with 20 millisieverts per year.
Amazing. Right on the nose.
Right on the nose.
Well, that is fantastic news. I mean, so there's some radiation shielding, but it's minimal, right? It's similar to what we have on the ISS now? Or?
Oh, no. Without a planet or anything like that, at Earth distance from the sun, it's about 462 millisieverts per year.
Okay. No, that's not what I'm asking.
Oh, okay.
In orbit around equatorial low Earth.
Right, yeah.
There is some shielding, but it's just like the thickness of the walls, right? It's a few centimeters of aluminum or something.
Well, I did another study that. Well, let me make a point before I get to that.
Okay.
Is about 50% of the galactic cosmic rays, which is the ones you're most concerned with, are blocked by the Earth itself.
Sure, because you're right there.
Right, exactly. And the closer you get to the Earth, the better job it does of protecting you. Then the magnetic field, electromagnetic field, is also it's at its most protective when it gets near the equator, and also the lower it is, the more effective it is. Well, I mean, the thing is, just consider water is an excellent medium for stopping galactic cosmic rays. It's really first class. And your life support system has a lot of water in it. I mean, you start calculating how much you need for different crops and stuff, very, very quickly get a very large number. Okay.
So are you saying that I'm going to bring the image up again, like this Kalpana 2 type structure. So you're saying that the entire exterior would essentially have a layer of water on it, like in the pipes, or
that would be like I'm saying is you're going to have the life support anyways.
Okay.
You have big tanks of water, whether you have any radiation or not. But you could place them strategically so that they contributed to the radiation shielding.
Right.
Okay. And I actually did one study where I ran Altaris from the earliest data it had to the present. Oh, there's Kalpana Chala.
Yeah. Oh, let me stay on that. Sorry.
Yeah, actually, I named my settlements after Kalpana Chala, who you see right here. Kalpana was the first Indian-born person to fly on the shuttle. And she also happened to be in the office next to mine I worked. I
Oh.
was doing. She was doing computational fluid dynamics, and I was doing visualization of computational fluid dynamics. It was a natural synergy. I don't think we actually ever had any papers. I think it was all presentation materials for Mucky Monks and stuff for the shuttle. The unfortunate thing is that when she was coming home on the Columbia, it disintegrated over North Texas.
Yeah.
And killed everybody on board.
Yeah.
And there was this pile of flowers and tokens all about her for months in front of NASA Ames Research Center. She was she was the real McCoy.
Yeah, terrible loss. But I'm glad that you were able to honor her memory with this, this significant advance, that you've named after her.
Yeah. So it would be good if I could take a break in a few minutes, if that's all right.
Sure. Let's do it now. Eric and I can talk for a couple minutes, and
I'll be back in just a minute.
All right. Sure. Yeah. So it's really interesting to see, how Al has taken the concept of these huge cylinders and really taken it down a level to where we could actually imagine building one of these, maybe in a couple decades time. I mean, it's still large by current standards, but it's tractable.
Well, yeah, for space construction, it's large, but I think you made a really good point that you look 100 years ago, and we were barely had flight at all, and to see where we've come from there, and we did not have digital computers, and 200 years ago, the technological progress has just been staggering, and I can imagine as we get more and more people on Earth, this will become a bigger and bigger issue, not just about space exploration, but for the health of humanity in a way. And so, yeah, I agree with you. I wouldn't be surprised if we start seeing, these large scale settlements in decades time.
Yeah, I mean, it's clearly not going to relieve the population pressure on Earth, or resource depletion anytime soon. But I think if we don't start, then we will have no chance of being able to migrate, right? So, and I think that the more we do things, we also lower the cost and get it more to the realm of the possible for everyday people, which I guess is the goal.
Absolutely.
Hello.
You're back.
Hey.
Yeah.
Hey there.
Revisiting the fact that we're not going to launch 7 billion people in the planet.
Yeah. Well, you're just sort of talking about if we don't get started, we'll never have that capability, right? So,
well, the Starship is a pretty good step in that direction.
Absolutely,
the SpaceX Starship.
So we can bring those launch costs down.
Yeah, I think that's the first enabling step, as you said. Go ahead, Eric.
We've talked a bit about the Kalpana space station design that you worked on, and my understanding that's also a rotating habitat to provide that artificial gravity or pseudo gravity. Can you talk a little bit about that? How fast does it need to rotate? How much gravity does that produce? Is the Coriolis effect going to be problematic for the general population? What are your thoughts on that?
Well, they are many and varied. The thoughts about basically there's a fixed relationship between radius and how fast you have to rotate. So the larger the radius, the smaller the lower the rotation rate needs to be. Okay? And people have thought for a long time that the big problem with rotation. In any case, if you rotate, you get a force. If you're through your spine and down onto your feet. That's a centrifugal force. And it's not a real force, but it feels like it is. And I should step back. Is the reason that the rotation is so important, and is very, very important to get the artificial gravity right, is that we have absolutely no idea what the effect of rotating artificial gravity or lack thereof has on children. None. We don't have one bit of data. We've got, of course, data on lots and lots and lots of people, at 1G, And we've got, what, 12 guys that went up, and they were all guys in those days.
Right.
That at 1/3 G, which is
Right.
and that's it.
Yeah.
Well, I've got
Right.
a fair amount of time on N0G.
Well, and so I'll ask the silly question, which I know the answer to, but I want you to respond. So, well, if we have lots of data at 1G and we have, many, I mean, more than 100 astronauts have been in space at 0G, right? And on the ISS the last 20 years, we've had dozens and dozens of measurements, sometimes for as much as a year or more. Why can't we just draw a line between those two endpoints and know what things are going to be like at a 3rd G or whatever?
The function may not be linear.
Right. Yes. And it may even have maxima or minima along the way, right?
Yeah. And we just don't know. The other thing is we have for the people you're most concerned about is the kids, right? Because they can't give informed consent.
Right.
And of course we got nothing. I mean nothing. In terms of data and growing up.
So what you're saying is, until we know more, it is prudent for us to always provide a 1G environment through this rotation effect in space if people are going to live there long term. Because if people decide to have children, or just if they want to spend the rest of their lives there, we don't really know the long-term effects of partial gravity on the human body, even if you're fully formed, but especially in children, as you're saying.
Yeah. And there's also, and that's all basically dead on. Then the thing people have said is, well, wait a minute, when you go into this rotating environment, you're going to get sick, and that's true, you will. But it turns out to matter for space settlement. It matters for a tourist. It matters for somebody who's going up there and is going to spend 2 days in space and come back, because that's all he can afford in his ticket. He only has $55 million.
So why does
but you're saying if you're
for someone who's going to live
if you're a tourist and you go there, it could ruin your vacation completely. You're filthy sick, throwing up, for 2 days, and then you go back. I mean, who needs that? But if you're going there to live, you'll adapt. And there's data on this. That's with adults, but it's shown. Oh, interesting.
Yeah, I wanted to bring this up because we haven't shown any interiors yet. And this, I don't know what the radius of this is, but it gives you an idea of how much curvature you might see living in one of these smaller cylinders, right?
The radius is 50 odd meters, 56 meters.
Wow. It's not very large. Do you know how fast this would be rotating to provide?
4 RPM.
Okay.
And that's to provide a full 1G.
That's to provide a full 1G.
People don't seem too uncomfortable. Of course, it's a drawing.
I think this is stock stuff. Like you can buy this over the internet. Person with white shirt. Kid with backpack and red shirt, and you go and you pick out what you want, and you pay your fees, and there you go.
Yeah, of course. But anyway, I brought it up mainly just because I wanted people to have a visual of how different it would look from walking around, a typical city on Earth. So, But anyway, I'm sorry to distract. Back to what you were saying about the rotation rate and what people
you get sick. You get sick, but you'll get better in a few hours, a day or two at most. And if you're going to go and live there for 20 years, that doesn't really matter. It's unpleasant, but so what?
So you're saying that people adapt within a few days or weeks, and
they will adapt to 4 to 6 RPM within a few hours to a day or two. Not everybody. There are people who are particularly susceptible, and it might be a good idea to spin them a little bit before you send them up.
Do some Earth tests before they spend their millions on it. Right.
There's something very, very interesting. They did all these studies with rotating rooms. They would put the people in a rotating room and they rotate it up to 1 to 10 RPM and stuff like that. And they did it at Skylab experiment. Skylab was a space station, the first space station that the Americans put up. Me and you, and and they did a rotation experiment. What they did, the procedure was put the astronaut on a rotating chair with the axis of rotation going through their spine. It's non-physical, so they'll be okay. And spin them between 1 RPM and 30 RPM. Okay. And just to be fun, they made them do head motions. Now, if you are ever seasick, do not move your head. Okay. Under any circumstances. And they threw up, and they just, it's terrible. Then brutal. They did the exact same procedure in orbit on Skylab, and they were fine.
Yeah.
Their stomach bothered them a little bit. No big deal. Then they came back down. They went to the same procedure again, and they threw up and they felt terrible. And you had a question.
Yeah. So what's the explanation of that? So you've basically removed Earth gravity, but you still have this basically outward force. So your body feels like you're basically a spinning ballerina, is what you're describing, right?
Yeah. We don't have to spin that fast, but I have a different hypothesis.
Slowly spin.
I have a different hypothesis. My hypothesis is that if you look at it, it has to do with the complexity of the vector field you're in. You can describe the gravitational issues around this system with a vector field, little arrows pointing in the direction of the gravitational force at every point. And if your brain looks out and it has otoliths in the inner ear to sense force and gravity. So if the otoliths say one thing and the eyes say something else, the brain goes, this is my hypothesis, we're in a village in Africa, a million years ago, and we just got some meat in, and it's making us all sick, so we better stop and we better get rid of everything that's in us. So I'm going to upchuck, and that's going to get everybody else to do it, and then this tribe will survive. Right. Hypothesis. Okay.
Right.
And so with that hypothesis, you would expect to see more complicated vector fields result in longer sickness than less complicated vector field. Now, when you're in orbit, the vector field is a pure rotation. That's it. Right? If you're on, if you're in a rotating environment in space, if you're rotating on Earth, on Earth, you have the rotation and the force of gravity. So you have a more complicated vector field. The brain is unable to figure out what it is. And just to be sure, made the whole tribe upchuck their
right.
So that
make sure no one's poisoned.
Yeah. That kind of points to the fact that trying to do some of this research on rotation tolerance on Earth is going to provide misleading results, and we might not really have a good feel for the rotational tolerance of humans until we have some of these structures in space and can actually test them out. Is that right?
As a friend of mine, Joe Carroll, who has done a lot of work on designing a tethered-based system for doing rotation research. He's way into rotation, and and he's got a system where you can move around. And one system you can have a 3rd G, a 6G, and 1G. And it turns out, and this is really interesting, and another argument that this whole solar system is architected by some super brilliant engineers who we can't find. All of the useful surfaces on the different moons and you can cluster them all around 1/3 G, 1/6 G, and 1G.
Right.
Now I haven't seen this.
Let's list.
Let's
list what those are. So Venus and the Earth have about the same G, as well as Saturn, Uranus, and Neptune. People don't realize this, and of course, there's no solid surface. Right, they're so big, but they have so much more gravity. If you were to float in a balloon in the atmosphere of any of those 3 planets, you'd experience roughly within 10% of 1G also. Yeah. But then what about the others, the 1/3 G?
Well, they cluster around 1/3 G.
Okay. Like Mars, for example, right?
Mars.
And I think Mercury also is close to that.
Exactly.
Yeah.
And so
then you've got the moon at
what are the odds of that?
Yeah.
Okay.
That's really
Well,
another strange thing is, I shouldn't go down this rabbit hole, but I just have to. Oh crud! I lost track of what I was thinking about. It was fun.
rabbit hole avoided.
Yeah.
Actually, that's
Yeah.
fine. We're starting to get to the end of our time here. I'm just wondering if we might have any questions that have come in from the
Well,
chat.
yeah, we've had a
Eric?
couple, but we've been able to cover those so far quite conveniently. So Tom Spilker mentions that 6G is our moon, but also Titan, one of the moons of Saturn.
Yes.
And I actually did want to ask Al a question myself. We've talked a lot about some of the technical, aspects here, and we've kind of hinted at, some of the drivers. But I really want, in your words, I want to know, why do you think that we should settle space at all?
Two reasons: survive and thrive.
Mm-hmm.
Okay? Earth is a single point of failure, not just for our civilization and our species and the species that are associated with them and all the other species.
Mm-hmm.
But we face on this planet, we face extinction events from time to time. One of them got 95% of the species of dinosaur wiped out in seconds. It's believed that the atmosphere may have caught on fire. And there are at least we can detect the silly asteroids. Okay, at least we can find them and we can potentially divert them. But what are we going to do about a supervolcano?
Mm-hmm.
There's supervolcanoes that bury whole continents in 50 feet of dust.
Yeah.
One of these things is going to get us sooner or later, unless we spread out.
Right.
So that's the survival. You go ahead.
Okay. Well, maybe I'm putting words in your mouth, or it's your next point, but also human beings have been expanding for the last couple thousand years, and although our population is slowing, our appetite for resources and honestly for room is growing. And so I feel like being able to provide new land to explore and settle on would do a lot to relieve those evolutionary pressures to want to go forth and prosper, I guess.
Yeah. Well, remember I said survive and thrive, and what you're talking about the thrive bit.
Right.
Now, to get an idea of how much you can thrive, is the total amount of energy available in this solar system is on the order of a couple billion times more than the energy budget of Earth.
Right. So from an energy argument alone.
So let's just say we got plenty of energy.
Yeah.
If you next thing you do is you take the asteroids, you don't touch any moons, you don't touch any planets. You take the asteroids, you tear them apart, and you turn them into O'Neill cylinders or something along those lines. And you get somewhere on the order of a few hundred to 1,000 times the surface area of Earth, depending on your assumptions about radiation shielding and so forth and so on. In other words, vastly enormous. We don't have to use anywhere near all of that, but that just gives you an idea of how good it should be. There's one thing I would like to do before we run out of time, is I would like to sketch my vision for how we build the first space settlement.
Oh,
yes, please.
Please do. Yes.
Okay. So the basic idea is that you can take advantage of that sweet spot at 500 kilometers near the equator to get rid of the radiation shielding. Now we're down to a system that weighs about 8.5 kilotons as opposed to 3 or 4 million tons. If we rotate it fast, if we rotate it about 4 RPM, it shrinks down to about 100 meters in a dimension. And if you put those two things together, you get this massive reduction in cost. And furthermore, you get a small system that you can build and you can develop more and more better ones incrementally. Even better, before you even start building any settlements, you can build hotels. They don't need radiation shielding. You don't run them through the South Atlantic anomaly. And once you build a couple of hotels, you can make them bigger and bigger until they're the size of Kalpana 2, which is a 100-meter length and a 100-meter diameter, give or take a bit. And then all of a sudden, you have your first settlement. And my calculations on dollars, because this got lost somewhere back there, is is the way that you pay for it is the first thing is to recognize that this is a real estate business.
Yeah.
And what do you do when you want a house that you can't afford, that you don't have the cash to pay for? Okay, you
Take
get
out a loan,
mortgage.
right?
Okay.
Yes.
So the mortgage, it turns out, needs to be on the order of $4 million. Okay.
Wow, is that it? I mean,
Yeah.
that's not
Well,
what most people pay for mortgages, but I'm amazed it's so low because.
Well, yeah. I chose every assumption you could make and not be completely out to lunch. I made it as small as possible.
Okay. I would have expected $1 billion. So.
Yeah. So in any case, so you move in probably as a couple because there's not that much room for single. That's going to be a messy problem.
Are we talking about like a small Manhattan studio or what? Like how much room does a person get in this?
Oh, it's a little bigger than your classic Manhattan studio, but I can't remember exactly what the volume is. I mean, you can build it out in if you can accept some variation in the G, you can fill space with these things.
Mm-hmm.
You can have one cylinder at 50 meters, 56 meters diameter, and then you can have another one at 46 meters.
Build up towards the axis of rotation.
Yes, exactly. And at some point, like maybe the only people that go in just grandma and grandpa. Because, they get rid of their walker, right?
G, yeah.
Yeah. But you're basically saying that what I'm showing here is sort of on the order of what could be built, paid by ordinary people who maybe are a little wealthier than average, but their nest egg could buy them a permanent place on one of these things.
Yeah, my kids, my son recently bought a house in Silicon Valley. 4 million is, he did get something less than 4 million, but 4 million is nothing.
Yeah.
Yeah, not in some places on Earth for sure.
Now here's the great trick.
So are you saying here that? Sorry, are you saying that you could build a settlement by having these occupants buy in, get the mortgages and buy in, and then have that settlement built with that money? Then? Yeah,
that's the best to say basic idea. So this whole concept. So you can go out there, and where are you going to get let's just assume that you made the money in advance, a couple $1 million down payment. Okay.
Yeah.
Which is not a bad assumption. Now, how are you going to pay the mortgage? Well, the first stop is you keep your job. One thing we learned in the pandemic is you can easily telecommute 500 kilometers,
right,
to Earth to your job, and we're only 500 kilometers up, maybe 6, maybe 4.5, whatever. So you keep your day job. You don't even take your day job. So that's the first step, paying for it. The second step of paying for it is deployment of large satellites. Like the Webb just opened up, and it worked. Okay, it could have easily not, but it worked. And but it was a total nail biter. It was right. Every time it unfolded something or another, everybody,
Well, wait. So you're saying that a facility like this, because of its size, could build large satellites like the James Webb and then launch them to their rather than building them on Earth? Is that?
Well, I was actually thinking of that's actually an interesting idea. If you make it big, you have to package it for launch because there's quite a bit of vibration on launch, and you have to pack the whole thing together. So what Kalpana 2 people do is they go in and they pull out the parts and they stick them together and they do the tests to make sure everything's working. And if there's a real nasty problem, they actually send an astronaut out there with the whole suit on and everything. But most of their work is done teleoperating. Okay, so
that I can imagine them.
Go ahead.
Sorry, go ahead. I was going to say, so we're on this rotating structure that has Earth normal gravity, so you can work and make adjustments. But then when it's ready to deploy from Kalpana 2, instead of putting it through the vibrational hell of launch, you just gently lift it to the center of the structure where there's microgravity and push it out the airlock, and it's on its gentle way, right?
Yeah, there's all kinds of great scenarios you can speak.
Yeah.
So in any case, okay, once you do that, Now you're off to the races because you can build more and more of them. Oh, and there's one more step, is just, you want to have more than just keep your day job as a requirement for this. And the obvious one is to build large structures. And something like the web is great, but it's a one-off. Okay, you do it once, and you're not going to build 30 of them, or 50 of them, or 100 of them. But if you're in the safe space solar power business, you are, if you're going to make it work, you are going to make thousands of them, hundreds, if not thousands, of gigawatt class. If you want to replace the fossil fuel production of energy on this planet, it's a big job. So now, if I was given an enormous pile of money and told to go build space solar power satellites, I would not build Kalpana 2 first, right? Because it just makes it too hard. But if Kalpana 2 was already there, already inhabited by a bunch of people living off of their remote work, right? That's a whole different story. All I have to do is hire them. I only have to hire them and have something to do, right? And those people are going to go, this is my chance to get into space, baby. I'm out of here. And so,
I was going to say they're already in space, so you don't have to pay for their lunch, right?
Exactly.
They're there.
They're there, and they have tools, and they have bolts, and they have screws and nails,
and machine shops, and maybe even a small foundry, and
all that sort of stuff. So, okay, then you're to that stage, and then it's kind of off where you want to go. But you work through the solar system. We kind of learned how to do that. We looked at getting from one star to the next, which is very difficult because the distances are really quite large. And you have to have a source of energy. But it's plausible. It can be done. And in terms of matter, there's actually I see bolides out there all over the place, and there may be some overlap between ones that are originally part of Alpha Centauri and other ones part of Earth. So you get that far, and then if you can get from one star to the next, then you can get to most of the stars in this galaxy because it's we're kind of on the outer edge and things are kind of far apart. So now the trick is, how do you get from one galaxy to the next? And there's hundreds, I believe the number is hundreds of billions of light years apart. Oh my God.
Well,
so how do you do that? Okay.
You have an answer? We can save that for another
I'm telling
episode.
you how it is. There are some galaxies which, just because of what they're doing, will get a particular solar system or group of stars in a position to get slingshotted out to the nearest galaxy. Okay. Now, you've already spent 1 million years perfecting your recycling. Okay, so it's really good. And
these people are basically a nomadic civilization here, right? If you're talking about a civilization that's traveling between the stars, they don't really care where they go, as long as it's an interesting journey, I suppose.
So you can get that. And then eventually it'll be heat death of the universe, right? Who knows? With 5 billion years of technological development, maybe we can actually
do something.
That's kind of stretching it to put it mildly. But if you had 1 million years of scientific development at the rate that we've been doing it for the last couple of centuries, you'd know a lot.
Yeah.
And even if it never works and it's completely impractical, it's fun.
Well, I love how we went from like the very first steps of space hotels where people stay for a couple days, to the first permanent structures where some fairly wealthy people might be able to retire there. And then I missed something in the middle. Suddenly we were talking about intergalactic travel. So you certainly have a very flexible mind, and you've thought about
Well, I think the interesting point is that the actual habitat, right? These O'Neill cylinder scale communities are going to look very similar when they're around Earth, when they're in the solar system, when we're at other stars, and even traveling between galaxies. The fundamentals of supporting human life like that are going to be very similar.
And it frees you from the dependence on a planet. All you need is some garbage. You need some asteroids, some comets, stuff. You don't need any particular you need the right atoms. But,
Yeah.
you know, again, after 1 million years of development, you'll be able to take pretty much anything and put the atoms where you want them to go.
Probably.
In 1 million
Yeah.
years, yeah.
Well, sure. In 1 million years, pretty much anything is possible. It's
Well, this,
I think the question I have for, you know, for sort of the foreseeable, like, let's say the next 100 years time, and even that might be looking too far in terms of what we can reliably predict. But I guess my question is, I understand that you can get a pretty good closed loop life support within a cylinder, but it's still a pretty small number of people and, you know, area to work. And if you're trying to be able to make everything, essentially your entire industrial, you know, modern civilization, my inclination is that you're certainly going to need a community of these that are specialized in different things. You might have cylinders that are entirely industrial and they just make integrated circuits and, you know, lightweight aluminum structures for vehicles, and there's a chemical factory. You know, the point is that there's a bunch of these that if they're going to travel to another star system, they would have to go as a group. And you might have 100 or more of these all traveling together rather than a single cylinder sort of off on its own.
oh yeah.
Anyway, that's kind of my
you definitely want the
instinct
redundancy
about
of
it.
multiple cylinders. There's no question about it.
Yeah.
Because things are going to go wrong.
Yeah.
They always do. And you need overcapacity, you need more capacity than you actually need at any one particular time, because you're going to have spares. You know, what if you have a crop failure?
Right, exactly. Yeah, or you have that puncture that you can't repair and you have to evacuate people. Where do you put them? Right, you have to have some other.
But that's one nice thing about the Kalpana series. You know, in small, close, and low Earth orbit, is we can work out the problems. You know, if thing goes wrong, things start going south, and you know, you're only 500 kilometers from Earth. You know, you pack everybody up in starships and you fly them home.
Mm-hmm.
Yeah.
I mean, it doesn't mean you'll be able to do that for every possible disaster, but you'll be able to do it for some.
Yeah.
And it's going to be a situation where you have much more control over the risk, and at the same time, you get that survive and thrive business. You know,
right,
comes along with it.
Exactly.
Yeah.
Well, I think this might be a good time to mention that Al, in addition to being a very creative engineer and, you know, analyst over the years, he's also an accomplished musician. And Al, I think you said that you might have a song to play for us today.
Yeah, I have to make a little trip, and I will be back very shortly.
Okay.
And I will. I got a tune that I practiced up a little bit.
Great. We'll wait for you.
Yeah, I think that's
All right,
exciting.
great.
It's
What a great treat.
Yeah, a lot of really interesting thoughts there for sure. And I love it that
I didn't think he was going to go in.
Yeah.
I wasn't expecting him to go intergalactic on us.
But yeah,
that definitely stretches my brain.
All this technology that we can develop now, you know, will have a long-lasting impact for humanity, you know, into the future, even, you know, as far out as we can kind of imagine at this point.
Yeah, and I think I'm glad he brought up the roadmap, because it really does lay out, you know, there's a lot of gaps, of course, that have to be filled in, but it really does lay out a possible path to a self-sustaining
to our future,
you know, structure.
Space, really.
Right.
You know, I mean, that's kind of
what
we're here in a way, is like looking at what are the aspects of that roadmap, and I think Al brought up a lot of really great points therein. You know, how do you, from a habitation standpoint, how do you get there?
Right. Yeah, and I'll just say for the listeners, you know, in future weeks, we're going to be talking with other people who will be bringing other dimensions of this problem to bear, which I hope will start to flesh out the idea of how do we get there. And we won't have any definitive answers, but we will certainly be asking that question many times. So,
yeah.
All right, Al looks like he's back. I'm going to bring him back. And Al, I will give you the floor.
What's that?
Yeah, why don't you go ahead and play a song?
I'm giving you the floor.
Why don't you come down to my place? I would like to give you just a little bit of what I'm thinking. Yes, I'm thinking about you.
Wow, that was
Oh, wonderful.
fantastic.
No, I'm glad you liked it.
Thank you
Absolutely.
so much. Yeah.
What a great way to wrap things up. I'm really glad I asked you ahead of time if you could play us the song, because nice. Hope the audience enjoyed it. I hope it came
Yeah,
through okay.
me too.
Yeah. Well, this has been a really fun hour. I really appreciate all of your careful work over the years and the way you've been able to explain things so clearly to us. I had a really great time. Eric, I don't know if you want to add anything.
Yeah, such a great conversation. So we really appreciate you coming on and talking about our future in space and leading us down this technology, but also thinking about that roadmap, how we can get there.
No, thank you very much. I mean, there's nothing that's really quite so fun as to talk about space.
Yeah.
I think we agree. All right. Well, be well, Al. Maybe we'll be talking to you again in a few months' time. Otherwise, keep in touch. And thanks for tuning in, everyone.
Yeah. Good to see you.
All right. We'll see you next time.